What I'd like to do next is go through a few examples of problems to calculate KEQ for a few of the example problems that you have that you should have picked up in class to work on for this. First of all, we'll just set up a few what we call KEQ expressions, which is basically setting up the calculation for doing the actual math, but not putting real numbers into the positions of the variables in the equation. So what I'll do is take you through a few examples from the pages that you do have, and then we'll actually go on to solving a few problems from the next page or from the back of that same page to see if you know how to set a few up and then plug numbers in and run the math through to calculate for various variables. So the first one to look at here is number 1 on the Introduction to KEQ Problems page. It's a really simple looking decomposition reaction. Basically you have PCl5 decomposing into PCl3 and chlorine. So what I'll do here is just kind of help you set up the expression. And again, basically what that means is we're setting up and putting everything into place as though we were going to plug numbers in next. And for KEQ, if you recall, again, this is our KEQ equation. Products go on top, reactants go on the bottom. And don't forget that we only use solutions and gases. So for that equation, we want to look at it first and consider these states. I've got a gas, and another gas. So everything involved in this equation will be part of my KEQ calculation. Secondly, you want to balance your equation. It needs to be balanced first because those coefficients become our powers on our calculation. So to balance this equation is really quite simple. This one's actually balanced with all ones, but I want to go through and make sure that I do that. And this is where reducing things matters. So if for some reason you balance this using 2, 2, and 2, it would still be balanced, but it wouldn't be simplified. And the difference is then that those 2's would become squares in your powers, and that would change your answer in the end. So to calculate KEQ, we would set up the expression, and that's all you're being asked to do on this page. KEQ is products over reactants. Products multiplied together over reactants multiplied together. And again, using only gases and solutions. Well, here we have all gases. So my two products are PCl3, so I'll put that one on the top, PCl3. And remember, we use square brackets to show the molarity of PCl3. Now there's a 1 in front of it here, so that means this is taken to the first power. As you know in math, the first power is sort of the default. So if you're working with power of 1, you don't necessarily even need to show it, but we'll show it just for establishing that habit. The second product is chlorine gas, and it too has a 1 in front of it. So I will put chlorine in as the second value on the top, and we'll be multiplying those two together. Again, this is a power of 1. So it's PCl3's molarity times chlorine's molarity. I got a lot of people who will take this plus sign from the equation and put it in here between the two. We're not adding them together though, we're multiplying, and that's an important difference. And then the reactants go on the bottom. Well, we've only got one reactant here, and it's PCl5, right? So that's the only thing that can go on the bottom of my calculation. So I'll put PCl5 in down here. And again, I put it in square brackets as molarity to the first power, okay, like so. And that's the expression. That's all you need to do for number 1, is to put products on the top, reactants on the bottom, and because we don't have any numbers, we can't put anything in here and actually calculate it, but we'll start to do that on a couple problems here in just a few minutes. That's the expression, that's your finished answer, products over reactants, and for gases and solutions only. Let's do another one. This is number 2 on the same page, the very next item there. And again, we want to consider gases and solutions. Well, I have a gas combining with a gas to form an aqueous solution, so everything in this equation will be part of my KEQ expression. Next, I want to balance my equation. Well, to get it balanced, I'm going to need a 2 in front of my product, hydrogen iodide. And so one of each of these will combine together to make 2 of those. To set up the KEQ expression, same idea. We want to take products over reactants. Well, in this case, I've only got one product, and it's hydrogen iodide. So I'll put that on top, and again, it's the molarity, so I'll show it in square brackets. And the 2, that's a coefficient over here, becomes my squared 2 here. Make sure to keep those in mind. And then I've got 2 reactants, hydrogen and iodide, or rather iodine. So hydrogen and iodine are both products, are the reactants. And so they go on the bottom. Reactants are always in the denominator. And each of those is to the first power. Hydrogen iodide squared over the quantity hydrogen times iodine. The 2 of those multiplied together, and each to the first power. That's as simple as it is. Setting up the expression takes nothing more than that. Okay? And to do the calculation, we would put some values in there, square the top one, and leave the other ones to the first power. Again, we don't have any numbers here, so we're just setting it up as if we're getting the problem ready for actual use. Okay? Finally then, let's take a look at number 5 on the same page, one more example. And the reason I choose this one, as you might be guessing if you look at it, is that there's a solid involved. And so when I set up my KEQ expression, I want to actually use carbon as a solid as part of the math. However, we do need to use it as part of the balancing. We need to balance the equation before we stop looking at solids or liquids. And so this is one carbon and then another one on the left, so 2 carbons and 2 oxygens, which means we're going to need a 2 over here. So 1 carbon and 1 carbon dioxide will combine to make 2 carbon monoxide molecules. Now when I go to set up my KEQ expression again, because carbon is a solid, okay, this solid, we omit this when calculating KEQ. So we omit this when finding my KEQ and setting up the expression and so on. We don't even bother using it. So we'll leave that one out, and we'll have then product. Well, I've got one product, CO. That's a gas. And I'm going to square it because there's a 2 in front of it. And I've got 2 reactants, but again, leaving this one out now, we're only going to have one left to compare, and that's carbon dioxide, like so. So carbon is left out. You don't see this carbon. You don't see this guy down here in the bottom of the equation, as it would be if it was involved. It's kind of left out as far as the math goes because it's a solid, and its molarity doesn't fluctuate. Solids don't have molarities that are represented meaning quite the same thing as we'd normally expect. Now, let's go on and do some actual problems. If you look at the side of that page, the first item there says to balance the equation and find the equilibrium constant, KEQ. If the sulfur dioxide concentration is 3 molar, the oxygen is 4 molar, and the SO3 is 2 molar. All right, well, to set this up, first we're going to need to get our equation balanced, right? And so to do that, we've got SO2 combining with O2 to make, in an equilibrium reaction, so two-way arrow, SO3. And to balance this equation, we've got 1 sulfur on the left, we've got 1 on the right, we've got 4 oxygens on the left, we've got 3 on the right. Well, we're going to need to get this 3 up to a larger number because we've got 4 on the left side. We need to get this 3 up to a larger number. Well, the next number we can go up to is by putting a 2 here. That gives us 6 oxygens. And on the other side, to get 2 sulfurs, I would put a 2 here, and that gives me 6 oxygens, 4 here and 2. So to balance this, the coefficients go 2, 1, 2. What I want to encourage you to do with these first few examples is to go ahead and just set up the expression first. So before you start doing the math, go ahead and set the expression up. Well, it's going to be SO3 on the top, that's my only product, squared. And then on the bottom, I'll have my 2 reactants. I have SO2, that's also squared, and oxygen to the first power. And again, watch those coefficients in the balanced equation. Make sure they show up in your KEQ expression. Now, let's do the actual calculation. Let's put the values in that we know. In this case, we're being asked to find KEQ. So that'll still be our unknown. That'll be our X, if you will. And so I'm going to write it just down here. It's KEQ equals, and then let's put in what we know. Do we know the SO3? Sure. It's right here at the very, very end of the problem. SO3 is 2 molar. Okay? So 2 molar. Now you can leave the molarities off as long as they are molarities, because in the end we can't multiply the m and have molarity squared. KEQ is a dimensionless quantity. In other words, it doesn't have units to it at all. But on the top, 2 molar is my SO3 concentration. So the SO3 value is 2 molar. That's dropped in there. SO2 on the bottom is 3 molar. So my first value here will be a 3. And again, it's got a square on it. And then finally, my oxygen concentration, my other reactant, is 4. Okay? So my oxygen will be 4 molar to the first, or just 4 molar. So I've plugged in the 3 values that I know. And again, we don't pay attention to the m's or try to keep track of molar squared or anything like that. We're going to leave the molarities essentially out as far as our math goes now. So I'm just going to kind of cross those off. And you can get in the habit of doing that or just leaving them off. But they need to be molarities before you can plug them in here in the first place. So very slowly here, then gradually we'll work this up. 2 squared on the top would be 4. On the bottom we have 3 squared, which is 9, times 4. So essentially we have 4 over 36, or if we reduce that down, 1 over 9. Now don't leave your KEQs as fractions. In the end, we want to divide that out and actually get an answer. So you can skip to the chase here, and essentially we get 0.1 repeating, right? 1/9 is 0.1 repeating. So KEQ is 0.11, 0.11. Now remember, if KEQ is greater than 1, it favors the products. Those must be larger values on this side of the equation than the reactants. But if KEQ is less than 1, as we see here, then we would say that the reaction is tilted back toward the left and that the reactants are favored. Well, look at the numbers we've got here. It makes sense, right? My product had a concentration of 2. My reactants had concentrations of 3 and 4. Those are bigger numbers. And so my KEQ value here, less than 1, means that in this equation, the reaction favors the reactants and is leaning toward the left. Now, if our job is to make a lot of money, okay, as far as making product and turning it into something we can sell for a profit, okay, then it's not good if our KEQ is small, right? Let me get this arrow out here, it's a little confusing. We want a KEQ that's large, and I don't mean like 10 or 15. We need a KEQ that's like 10,000 or 10 million. The bigger the KEQ, the more product you're making, and the more you can sell that for and make a profit if you're in the business of manufacturing some kind of products like this. So that's number 11. We come up with a KEQ of 0.11. If you think about significant figures here, you're thinking, oh, should that just be 0.1? That's fine. In the end, 0.1, 0.11, they're all going to tell us the same thing. This reaction is favoring the reactants because its value is less than 1 for the KEQ calculation. Let's take a look at number 15. Number 15 asks us to consider the reaction below, and here's that equation. With the equilibrium constant of 5.6 times 10 to the negative 2, that's our KEQ value that's been given to us. If we know CO2 is 3.1 molar, and hydrogen is 8.2 molar, and CO is 2.6 molar, what is the concentration of water? So they're asking us not to find KEQ this time, but to find the concentration of this. That's kind of our question to be answered. What I encourage, again, I'll ask you to do is set this thing up as an expression first. So KEQ equals what? Right? Products over reactants. Everything's a gas. Yep, we got gases all the way across here, so we can use everything. And is it balanced? Two hydrogens, a carbon on each side, 2 oxygens on the left, and 1, 2 on the right. So this is a very simple equation with just ones. Let's go through and label those so we don't forget that they're there. All right? And then I'm going to set my expression up. So water is a product that goes on top to the first power, or just leave it as it is, times carbon monoxide, the other product, to the first power. On the left side of my equation, on the reactant side, I have hydrogen to the first power and carbon dioxide to the first power. Everything's nice and simple when everything's to the first power. Now, as I mentioned before, as we're reading this off, the equilibrium constant is given to us. So we're not finding KEQ, we're actually given that here. That's often the case because it's kind of a constant we can look up and use. So I'm going to plug it in, 5.6 times 10 to the negative 2. If you don't like powers of 10, 5.6 times 10 to the negative 2, we can move our decimal over 1, 2, and that's actually the same as 0.056. So either one of those is okay as far as using it as KEQ. You could write it out as scientific, or you could use it as 0.056. Probably most people prefer the decimal version, but it's completely up to you. And you'll get the same answer either way. All right. Now, plug in the concentrations that we know and find the one that we don't. The one that we're looking for, the concentration you're being asked is, what is the concentration of water? You're thinking, water? How can water have a concentration? When it's a gas, it does. When it's a gas, it has a molarity. So that's our variable to be found. H2O's concentration or molarity goes here to the first power. That means we must know everything else. So carbon monoxide, CO, yeah, here it is, the last one. So that's 2.6. On the bottom we have H2. That one is 8.2. Okay, so 8.2 molar on the bottom. And carbon dioxide, my other reactant, goes in the bottom as well. That concentration was given as 3.1 molar. All right, so now we just need to solve for X, if you will, or solve for water. How you set that up, how you calculate things out is completely up to you, okay? Basically, to do this, you're going to multiply both sides by my denominator, right? So if we multiply both sides by 8.2 and 3.1, that'll get rid of them over here. Now, tell you what, I'm going to take my extra notation out from down below here and clean that up real quickly. Just kind of clean this out so we've got a little space to work. All right. Now, to calculate this again, if we want to multiply both sides by 8.2, and 3.1. Again, do the same thing to both sides, right? 8.2, 3.1, and we've got a third quantity here. That'll cancel this out, so that's gone, and this is gone. When we multiply 8.2 times 3.1 times 5.6 times 10 to the negative 2, we end up with an answer of right around 1.42. 1.4235. We're going to take a few extra digits here. And on the other side, all we have left is water, which is our unknown to be calculated. Okay. So water times 2.6. Notice I'm dropping the molarity, because in the end I know this has to be molarity anyway. It's not going to come from my math because the units aren't there to be calculated and canceled out. Divide both sides by 2.6, and that'll disappear. And in the end, we punch this all in, and H2O is molarity. When we divide that is 0.55. And so by knowing the KQ, we can find any equations, or rather any concentration for part of the equation by simple algebra. The water's concentration is 0.55. And you can always go back, plug it in, and see if when you calculate it out, it gives you the KQ value that you were given to start the problem. Now that's number 15. And the final example I'd like to go through then is number 5. Number 5 is on a different page, so it's on the other example practice problems that you should have picked up. And if you don't have it yet, you can just follow along with us and do this anyway. We're told the KQ value again, and we're being asked to find the NO here. Now notice my equation when it's balanced is 1, 1, and then this 2 is already written here for me. This is going to be a little bit different at the end of the calculation than the last one was, but not a whole lot more difficult. So real quickly then, let's set the KQ expression up. Remember, my products go on top, so that's NO, and it's squared. That's an important number to remember here. And on the bottom I've got nitrogen, and I've got oxygen. Each of those is to the first power. All right, let's put in what we know. 1.65 times 10 to the negative 3. You can use it exactly like that, or you can use it in its decimal form. And again, negative 3 means I move it over 3 times to the left, 2, 3. Essentially, that's 0.00165. That's 3 negative power. 1, 2, 3. 3 powers over, so 0.00165. Or you can use it as it's written, 1.65 times 10 to the negative 3. I'm going to go ahead and just use it as the decimal form for this one, just for something a little different. Doesn't make it any easier, but that way you don't have to bother with scientific notation. Now you're being asked to find our NO concentration. So that's my top value up here. And just because I'm finding it doesn't mean I don't still need to keep that square on there, so make sure you do. And on the bottom, I've got N2 and O2. Well, it tells me that my nitrogen and oxygen are 1.8 times 10 to the negative 3. And again, we can move our decimal over if you want. 3 positions here. Or we can write it as it is. Either way, it doesn't make any difference to me. And it should give you the same answer as long as you're punching it in correctly. Again, if you don't use scientific notation, it'll save you with parentheses and worrying about order of operations if you just change those into regular numbers first, but it's up to you. And the other concentration is here, 4.2 times 10 to the negative 4. 4.2 times 10 to the negative 4, okay. So I've got my numerator here, is where my unknown is that I'm trying to find. And on the bottom, I've got a couple numbers in scientific notation. Now, to get rid of those, we're going to multiply them over to this side, right? So multiply both sides by the quantities down here at the bottom. And when I do that, I'm going to have nothing left but NO squared, my nitrogen monoxide concentration squared. So I'm going to multiply both sides by 1.8 times 10 to the negative 3 and 4.2 times 10 to the negative 4. That'll cancel them out over here on the bottom, and I'm going to do the same thing over here. So 1.8 times 10 to the negative 3 and 4.2 times 10 to the negative 4, and my original quantity, and multiply all 3 of those together. Now, when I do it on this side, they'll cancel out, and this one too. It'll leave me just what I'm looking for squared. All right. So multiply this set of 3 values together, multiply all those together, and hopefully you'll find your answer comes out to be 1.247 times 10 to the negative 9. Again, that's just simply these 3 values on the left side multiplied all together. And on the right side, that's equal to my nitrogen monoxide concentration squared. Now, to undo a square, you have to do square root, right? So we'll take both sides and stick a square root of both sides here. A square root cancels out a square, and that'll leave you then with just my NO on the right side. On the left side, when I take the square root of this answer, it should give me something in the neighborhood of about 3.5 times 10 to the negative 5. And that's a molarity. Okay? We were finding the NO's concentration, and there it is, 3.5 times 10 to the negative 5. So we had to take a square root at the end. That's about as tough as they'll get. There are theoretically questions where you could be asked to find a cube root or something even tougher than that. We won't do any like that. I think we'll hit a square root as the hardest math, and doing the hardest reverse operations here to find an answer in the end. Just powers of 2. We could work with powers of 3 and 4 and other kinds of problems, but usually we won't want to find a third or fourth root to a problem because not a lot of students necessarily work with those very often, and a lot of people would have to ask a lot of questions or go do research when it's not important that you know how to handle those big powers, as they're not very common anyway. So hopefully these examples will help you out. Get to work on the others. Some of them are a little harder to figure out and might get confused and have to skip one or two, but work on the rest. There are several problems on the back of the original page, and there's a whole page of problems that you got separate. Do as many of them as you can. Try to do some where you're finding KEQ, and also do some where you're finding a concentration of one of the substances that's in the equation as well. And we'll look at the answers next week. Do your best, give them a shot, and if you have to, work through one, then check with someone nearby and see if you got the same answers. If you did, chances are you both did it right. And if one of you's got a different answer than the other, let's see if we can help each other find out where those mistakes might be. Good luck, and I'll see you when I see you.